Good morning, everyone. Good afternoon to people from India. I welcome you to this talk series CS Katha Barta, where we invite academics and professionals to deliver the talks. Our guest for today's talk is Dr. Pascal Welke. Dr. Welke is assistant professor for data science at Lancaster University. Prior to this, he obtained his PhD from the University of Bonn, Germany, after studying mathematics and computer science. Then he held the positions of postdoc in Bonn and at TUVN in Vienna, Austria. Dr. Welke is interested in learning on and with graphs, in particular expressive graph representations, as well as efficient similarity-based learning on graphs and graph kernel design. Today he will be speaking about expressive graph embeddings. I welcome you, Dr. Welke, and thank you for accepting our invitation. And I invite you to take the virtual stage and begin your presentation.
Thank you very much for the kind introduction. So I intended this. Also, thank you very much for the invitation. I'm very happy to speak here. I intend this talk to be somewhat of an overview over the field of expressive graph embeddings via homomorphism counts. So I will be talking, of course, partially about what I'm doing, but I also give a broader overview over this rather, let's say, specific topic in graph learning, right? So to get everyone on the same page, although I'd expect some of you to already be very familiar with this field. So what the setup that we're in typically, and in this talk in particular, is that we want to learn from structured data. So structured data typically, as far as I'm concerned, will be modeled as graphs. And here in this on the slide, we see an example of chemical molecules that were encoded as graphs. So graphs consist of nodes and edges, right? And here in this case, we make the nodes, these little round dots, to represent atoms in the molecule, and edges between these nodes correspond to bonds in molecules. So basically, we have a chemical molecule with some rings here and some things attached to that. And these are modeled in this way. So how does the learning come in? Well, we get a bunch of these graphs or molecules, right? And somebody tells us now that some of them belong to one class and some of them belong to another class. So for example, here these classes are represented by colors, and we want later on to be able to learn a function that takes these graphs as input and produces their corresponding label, at least with some good quality. So, and why do we want to do this? Because, well, conceptually, later on, it might be that we get new molecules and we want to predict whether this new molecule here in the middle is a blue molecule or is a yellow molecule, right? How do we do this? Well, in most recent years, let's say the last 10 years almost, people have focused on graph representation learning. So what is the goal of that? Well, the thing is, graphs on their own are a bit difficult to handle for most machine learning methods, right? So what people then tend to do is they take these graphs and they want to embed them into some typical higher dimensional vectorial space so that certain properties are maintained, right? What are these properties? Well, we want to have somehow that semantically and structurally meaningful distances are encoded. While these graph representations should be somehow interpretable and finally adaptable to given data. Why is this sensible? Well, in the end, basically, if we maintain meaningful distances according to what these molecules do, what in the end will happen is that we embed these molecules into, in this case, a two-dimensional space, right? And all the blue molecules should go somewhat close together, right? And also the yellow ones should also go somewhat close together, right? And now if we embed a new one, a new molecule somewhere in this space, given the function that we have somehow learned, and it turns out to be close to yellow molecules, we can somehow assume that this molecule of unknown class will be yellow in the end, right? And so this is why we want to somehow maintain distance structure of the underlying task. We also want this to be adaptable to given data because, well, the one task that I'm presenting here might be, for example, toxicity of this molecule. So are these poisonous or not? But if we have another task on the same molecules, for example, whether it's soluble in fat, for example, we might need completely different similarity structures. So all these requirements are somehow there, and we want to learn representations that maintain these properties. How is this typically done, or how would I argue that that we can look at this whole field? Well, typically we always have this process of going from graph structured data via a vectorial representation to the solution of your particular learning task. And in recent years, basically, people do this mostly via deep learning, where your graph structured data is put into something called graph neural networks that somehow are able to work on graph structured data and compute vectorial representations from them that we call latent space. Then you have some additional layers, a multi-layer perceptron, for example, plus a loss function, and you solve your learning task end to end by backpropagating the well, towards the, to minimizing the gradient of your loss function with all these weights as parameters. So that is traditionally, or that is like recently what people have done and are doing, but there are also other ways of doing that. Like in, I would say 15, 20 years ago, what people have done is that basically they solved a graph learning task via a graph mining step. Difference here is that basically there is a separate algorithm in this first steps to go from graph structured data to vectorial representations, where you'd specify certain types of patterns that you're interested in. For example, you look at, okay, which parts of the graphs appear frequently in my database, and you somehow enumerate them. And then you create feature representations, typically via incidence. So is this part that appears overall frequently part of my current graph? Then we put a 1 in the representation. And in this case, we get representations like this. Right, and then on top of that, you put your ML method of choice. Can be a neural network again, can be decision trees, can be whatever you imagine, right? Finally, there's a third dimension or a third direction of how to do this, which was 25 to 20 years ago rather famous, which is called kernel methods, where the adaptation to the graph structured data that you do is you design a kernel function, which is a certain type of similarity measure with certain additional properties. And then on top of that, you apply a kernel method, for example, support vector machine or kernelized ridge regression or lots of other kernelized methods, right? And the idea there is you design this similarity function to be able to work on graphs, and then the method itself is somehow independent of that the basic data was a graph. Although here you also have some sort of implicit feature representation. And so today's talk is about joining these things together in a sense. So we will be mainly working with deep learning methods, with graph neural networks, but homomorphism counts, as I want to introduce them to you, is somehow rooted in this graph mining area, and we will be combining these different views on graph representation learning. Let's start with problems, right? Because so far I've said what I want, right? And now let's see why this is hard. Um, if we want to go this step from graphs to graph representations to solving your learning task based on these graph representations, we need to well, specify what we want from our graph representations, right? And I would claim, and this to me this is supernatural, that we want to have two things. The first thing is that our graph representation functions should be permutation invariant, meaning graphs can be represented in different ways, right? You can rotate the nodes and you can rename the nodes and so on, and it still remains the same graph. So example, we have two triangles here, but unless we store some relevant information on the nodes, um, these two triangles are the same graph, right? So we want them, or we want our function to compute the same representation for triangles all the time, no matter how we input them into this representation, right? And the second thing also seems sensible, which is if I put two graphs that are not the same into into my graph representation function, I want this function to be, at least in principle, able to compute different representations for them, right? Makes sense. So the same stuff will be mapped to the same embedding, and different stuff will be mapped potentially to different embeddings. Why do we care about this? Well, think again about the structure, right? We go from graphs to vectorial representations to the solving of our learning tasks. If we, and in this case here, these two graphs are mapped to the same point, if we basically have that our vectorial representation cannot distinguish these two graphs, then whatever we do with these vectorial representations cannot distinguish these two graphs. So meaning we cannot get back what we lose in this first step. So if our learning task requires us to compute different target values for these two graphs, but we map them to the same intermediate representation, then we cannot do this, right? So we want, in principle, to be able to maintain this property that different things can go to different intermediate representations, right? Okay, so okay, we want that. Unfortunately, however, this is computationally hard, because what this means is that our graph representations somehow implicitly, or actually even explicitly, have to solve the graph isomorphism problem, because what I've specified is exactly the question of whether two graphs are essentially the same up to permutation or not. And we don't know whether this is efficiently solvable, right? Typical solution for graph learning now is that most methods that are out there drop this completeness requirement. So they allow certain graphs to always be mapped to the same representation, although this is actually not necessarily a good thing, right? So all graph neural networks that are out there, First-Feller-Lehmann tests, most practical graph kernels, and also all graph mining methods that I'm aware of, typically drop this completeness requirement. Okay, so how does this all connect now to homomorphisms that were in the title, right? Let's go with that. Let's first define what a homomorphism is. It's some way to measure whether one graph is part of another graph. More specifically, a homomorphism from H, let's say this triangle is H, to G is a function from the nodes of H to the nodes of G, such that edges are maintained. Meaning, if I map two nodes to nodes in the target graph and they have an edge between them, right, then the edge needs to appear in the target graph as well. So this is the requirement of an homomorphism. in contrast to subgraph isomorphism that you might know, there is no requirement here for the node mapping to be injective. So what we are allowed to do is shown in this lower example here, right? We are allowed to map two nodes of our input graph to the same node in the target graph. So you can basically fold graphs together into the target graph as long as the edges are maintained. Okay. Once we have defined what a homomorphism is, we can of course go a step further and ask, okay, if we have two graphs, H and G, we can ask how many of these homomorphisms exist from H to G. So example, this triangle again, how often does it appear as a homomorphic image in this target graph, or more specifically, how many functions from the nodes of this triangle to the nodes of this target graph exist such that they are homomorphisms? Well, in this case, there are 6 that map this thing to the upper triangle, because you can basically rotate this thing 3 times over, and then you can flip it and also rotate it 3 times over. And similarly for this lower triangle here, where you can do the same thing, right? So what we get here is that even in the simple example, there are already 12 homomorphisms from H to G. Okay, nice, right? So we have a way to, let's say, compute features for graphs. So this is graph mining, I would say, right? I mean, we are interested in homomorphisms, and we can now basically say, okay, we're looking for certain patterns and count how often they appear in a target graph. What this gives us immediately, and this is a very old result actually, is a complete graph embedding now. That is, if I were able to, for every graph, and there are infinitely many, I know, right? If I were able to count the number of homomorphisms from any graph to a target graph and create a very, very large vector of these vector counts, then 2 graphs are isomorphic if and only if these 2 vectors are identical. So this is a Lover's theorem from the 60s, and this immediately gives us a representation with the properties that I want, but this vector in its generality is infinitely long, and you can restrict it to finitely many elements, but nevertheless, this is completely intractable because there are too many graphs involved. So what we can do, on the other hand, now is we can count homomorphisms for some graphs in practice. The reason for that is that homomorphism counting is somewhat nicer than deciding isomorphism or deciding subgraph isomorphism, because it's fixed parameter tractable. That means there's a parameter called the tree width of a graph. I don't go into what this means, but the important thing is that if a pattern, so the thing that we are counting, has tree width k, then the homomorphisms from H to any G can be counted in polynomial time, where k, because it's constant here, goes into the exponent. So what this means again in our example, instead of this very, very long vector, we can just restrict ourselves to, let's say, the first few entries of this vector, create a vector where we only count those, and we have a tractable graph embedding that is somehow motivated by this theorem by Lovász, right? Now the question is, how do we select these patterns? Do we just, so basically, do we start from top if we can enumerate our graphs in a certain order, or what can we do, right? We have already observed that some patterns are more expensive than others, right? The higher the tree width, the more expensive it is to count them. On the other hand, now if we think about our learning task, some patterns might be more interesting or more useful for the task at hand than other patterns, right? So we have to now decide basically what kind of patterns are we counting. And we will see now two variants of how to do that. First of all, this paper by NT and Mehara from 2020 at ICML, I would say, started this whole interest in homomorphism counting for learning. Not necessarily true, but in recent years, I would say this is the fact. So they introduce these homomorphism counts as feature vectors of graphs. They also give the motivation via the Lovász vector and so on. And they propose to select a suitable and small pattern set F. So what does this mean? Well, they take the first 13 trees, so the smallest 13 trees, so you can enumerate them in non-decreasing number of nodes order, and cycles up to length 7. So start the 3 cycle, the 4 cycle, the 5 cycle, the 6 cycle, and the 7 cycle, meaning you have, what is it, 4 or 5 cycles, so less than 20 patterns that they used here. And then they use an SVM with these features. So they compute the number of homomorphisms from these patterns into graphs. This will be the feature vector for each graph, the representation. And then with that, they use an SVM to compute, to learn a function on top, right? And the experimental results here show that if you look at the top table, which are synthetic results which measure the ability of these methods to distinguish non-isomorphic graphs, because these graphs have as task to distinguish non-isomorphic graphs. You can see that on CSL and bipartite, this method works rather well. Although there is on this Paulus 25 datasets, it doesn't perform better than the other competitive methods, right? So it tends to be able to distinguish some of these graphs already quite well. And on typical benchmark tasks, let's say real-world tasks, we see that it doesn't necessarily beat the baselines of other of graph neural networks, for example, but it's somehow on par with the empirical results of those. So this was enough to somehow spark the interest into this field. And now, basically, what can we observe from this thing? In practice, although we have this nice theory behind it, that the full Lovász vector gives us a full, a complete graph embedding, right? In practice, this approach requires a fixed and user-defined choice of the pattern set. And what this means is, and if we now look at expressivity of this whole approach, this allows us to bound the expressivity of GHC by an extension of the Weisfeller-Lehmann algorithm. So, namely by KWL, where K is the maximum tree width of the patterns that we look into. So there is a clear upper bound of what we can distinguish. So meaning there will be always graphs that are different, but they will be mapped to the same point, and we can formally define which of these graphs these are, right? So, and with that problem now we set out, or with these two problems, user definability and this upper bound, we set out to extend this a little bit and came up with expectation complete graph representations with homomorphisms that we presented at ICML 2023 with people from my group in Vienna at the time. So what we do there is basically, again, the expressiveness of all methods at this point that we saw were somehow bounded by this KWL. We had GHC, which is strictly bounded by that. We have message passing graph neural networks, which are bounded by 1WL. And we have higher order GNNs, which are also typically restricted by some KWL. right? And conceptually, what this means is that the second you decide for an architecture, you also decide on a fixed upper limit of what kind of graphs you can distinguish. So so you restrict yourself to a certain level of incompleteness. Um, and that might be not good if you don't really know anything about your data sets, right? Because if you you don't know basically what kind of level of expressivity you need for your data set, but you have to, when choosing your architecture, basically implicitly say, okay, this is where we go and no further. So can we change this? And the answer that we came up with was yes, we can actually. And we presented an architecture that has no strict upper expressivity bound. And we'll go into why this is the case in a second. And additionally, asymptotically, our representations are complete. And this, at least in my view, allows us to adapt to these situations where we don't really know how much expressivity we need for our given problem, right? And it works well in practice. So the main idea was, what if we keep this completeness that everybody drops in expectation? What does this mean? Well, it means that we now interpret our graph embeddings as random variables. We say we define graph representation phi x that depends on a random variable x drawn from some distribution over some set. Okay, and then we call this graph representation complete in expectation if, well, the expectation over these draws of this random variable is a complete graph embedding. So if the expectation fulfills the requirement that we want, right? Why is that good? Well, because this means basically if we sample more and more of these variables, so in a sense, if we make our representation higher and higher dimensional, eventually this joint embedding will be arbitrarily expressive. At least there is no bound on this expressivity of this joint embedding, right? So you can imagine this like this. Okay, here we see basically the set of graphs that are distinguishable by 1WL and then by 2WL and so on, right? And what we do is, well, with the first sample, we get something like this, and then with the next sample, we get something like this. So it gets larger and larger and so on and so on and so on, right? And eventually we can cover this whole space, and there's no upper limit on this. And now that we have this, we have to think about how to do this efficiently, right? And again, recall this homomorphism counts, right? We have this vector that, if we take it completely, will give us a complete graph embedding. And so basically what we do is we design a sampling method such that the expectation of the sampling method is this full Lobas vector. By basically sampling individual dimensions of this vector. So, and then we can basically increase this according to our requirements. Why is this efficient? Well, the expectation is complete. Yes, this is fine. But why is this efficient? Well, again, because homomorphism counting is fixed parameter tractable. And what we do is we design a distribution that weighs down these expensive patterns. So basically, we take patterns that have low tree with the high probability and patterns with the high tree with the low probability. And with this, we can come up with our main theorem that computing expectation complete graph embeddings takes polynomial time and expectation according to one particular distribution that we have designed. We also showed in this case that there are convergence results to the Lovász vector and universal approximation results, which are always nice to have. So far, this is not really connected to graph neural networks, but what you can do, of course, is you can make any graph neural network expectation complete by basically computing these homomorphism counts with our method and gluing them to the final graph representation that we obtain by a message passing graph neural network, for example. And then in the end, obtain a full a representation or a architecture that is expectation complete. We see some empirical results that it works basically in this previous example, right? I mean, we can look at how does the empirical performance change if we compare only the upper part basically with this combined method that we have. And we see that basically in most of the times, the combined part beats the baseline where we only look at the upper part. So we also see on synthetic data that we are much better than these baselines, also than GHC in particular. Open question, of course, is the runtime is polynomial in expectation, but realistically, you cannot sample too many patterns because we compute this exactly and this takes some time. We have seen that it's enough in practice to do this with 20 to 100 patterns, but of course the question is, can we do more? And some recent developments that I just briefly want to mention is that we can speed up this runtime while maintaining the properties by estimating these homomorphism counts instead of computing them exactly. And there are some references that where we investigated that and also related work that looked into that. Tends to be fast and rather precise in practice, so this is a good way to go forward with making this like a real practical example. Next, I want to continue with homomorphism counts as node representations, because so far we have used them as graph representations, right? We have counted how often one graph appears in another graph. That is on the global level on this graph, right? But we can also localize this. And the reason why this is interesting is that so far message passing and homomorphism counting do not really have interacted, right? We have just glued stuff together on the final layer and be done with it, but you can actually also include the homomorphism counts that you get within the message passing and pass them around in the graph. And this might help you with expressivity and also with practical performance. Right, and for this, what we need to do is we need to somehow localize homomorphism counts. And one way of doing that is that we look at rooted graphs, where we have a graph with one particular special root node V. And then we say a rooted homomorphism from one rooted graph to another rooted graph, well, is a homomorphism where we map root to root. So how does this look like? I have drawn the roots in black here and the other nodes in white. And so it requires that the black R goes to the black V. So you can do this basically like this. Right? And so now we can count, of course, in a similar way than before, rooted homomorphisms for any node V in a graph. So, for example, if we have a rooted triangle, there you go, we can see basically that if we basically now take every node of this little graph here as a potential root, we see, okay, we can embed this to this node twice, to this node twice, to this node twice, but to this node we cannot, because triangle cannot be mapped to a single edge. So this is now how another work by Barcelo et al. Exactly does this. It, in contrast to the previous method, what it does, it computes these rooted homomorphism counts in the beginning, adds them as node representation information, and then message passes this all through multiple layers of message passing neural networks to obtain an architecture that looks like this. This architecture is immediately more expressive than the Weisfelder-Lehmann algorithm itself, and is interestingly incomparable to 2WL. Can, however, be bounded by something that is called FWL that I will not go into detail. Experimental results here show us that this tends to work well. Again, this is a comparison against the baseline, right? I mean, you have here in the first column, you have the quality of the neural network alone, and in the middle column, you have the quality of the neural network where you add these node information, and you see that this typically improves, right? And then they also compare it with another method that it's not super relevant right now. Similarly, you see that typically adding these patterns also on real-world data sets and other real-world data sets typically increases the performance, but not necessarily statistically significantly. So that works as well. But what are the insights here? Well, conceptually, nice thing is by adding these homomorphism counts to the node labels before message passing, we get an architecture that is at least as expressive as message passing. So we certainly increase the expressive power. The second thing is, if you look at what they actually added, they added cycle counts. So we've seen cycle counts here, and we've also seen cycle counts in the previous example. So cycle counts seem to be important, right? And this is, sorry, I see I'm a bit slow. I have to speed up a bit. Cycle counting seems to be important, and this motivates basically the next work that I want to go into, where we identified again this basic problem, right? 1WL is sometimes not expressive enough. Specifically, it is insensitive to cycles because there are these examples where, like, every message passing graph neural network has to compute the same representation for these two graphs that are obviously different, and in particular have different numbers of cycles. Up here there are 2 5 cycles, down here there are 2 6 cycles, and still these methods have to compute the same representations for these graphs. So this is an issue, and then we also run into the issue that higher order graph neural networks are typically impractical to compute because it takes too long to do that. So this motivated this paper that we presented last year's NeurIPS with some people from Munich that I worked with, and the motivation here was that these cycle counts are rather important for chemical molecules, right? Because cycles have certain properties. You want to be able to learn from this. So what we do is we propose there a generalized message passing architecture that can distinguish graphs with different cycle counts. And now this is why it's relevant to this homomorphism counting setup. It can homomorphism counts all are cactus graphs that is more expressive than 1WL, and it produces again good results. What we did there, just very briefly, is a new GNN architecture that is parameterized by a cycle length and efficient on sparse graphs. And so what we want to be able to do is we want to be able to compute different representations if the cycle counts up to a certain specified length are different, right? I mean, so these two graphs here, so these two graphs have the same Weisfelder-Lehmann representation, but they have different number of 4 cycles, for example, this time counted as subgraph isomorphism, right? This thing down here has only 1 4 cycle, while the graph up there has 5. So we want to be able to compute different representations for these two graphs, and we want also to be able to homomorphism count certain things that are called cactus graphs. The cactus graph is basically a generalized cycle graph where you are allowed to glue together multiple cycles in a global tree structure, so something like this. The implementation basically works as normal message passing, if you are aware of how this works. Basically, if we want to compute the new representation of this node V, what we do is we compute a function that depends on, well, the representation of the node V in the previous iteration on the representations of the immediate neighbors. That is this. Right, and then we include also the free cycle neighborhood, because this V is contained in this free cycle here and in this free cycle here, and potentially also like larger neighborhoods like the for cycle. We can enumerate this quickly, and specifically on chemical molecules, this is easily be doable. And we can compute complete representations for these cycles using traditional GNNs. So overall, we can construct an architecture that is as expressive as a certain Weisfelder-Lehmann variant that considers all these extended neighborhoods. So we have a nice result that we can learn from these extended neighborhoods. Basically, now if we look at empirical results on QM9, for example, we are able to beat current rather well-performing methods. And also on the zinc dataset, there is also one very standard common benchmark dataset. We actually currently achieve state-of-the-art results. So open questions, we have seen different hierarchies of expressiveness. Some of them work well, some of them work rather well. So we have seen that we can increase the size of this pattern set in the GHC, and also in the expectation complete setup, where we basically make pattern sets larger that we count globally per graph. We have seen these localized things where we also get a certain hierarchy that makes more and more expressive depending on how many patterns we count locally. And we have this R-loop PWL test that I presented in the previous slides. What exactly do they have to do with each other, right? How are they connected? Can we collect most of our results in one architecture? And the answer is, interestingly, yes. And this is a recent, very interesting result, which also was presented at last year's NeurIPS, which is basically, instead of adding the hom counts in the beginning or in the end or somewhere in the architecture, we can change the architecture, so these layers, in such a way that we can represent all of these previously shown methods within one abstract architecture, right? And the reason for that is that method passing can be generalized to homomorphism counting. Just very briefly, if you are interested, we can discuss about this in the questions, but there is a even more weighted variant of homomorphism counting, where we can basically introduce node weights, and where we basically compute a generalized count that, instead of counting each node exactly once, we count each node as often as the weight basically defines. And now the step to make a learning architecture out of this is that we can replace these node weights by learnable functions that compute these node weights and train this basically through this whole architecture. So, and then basically what this allows us is that suitable pattern sets in each layer, we're counting the homomorphism counts, these weighted homomorphism counts for certain pattern sets, allow us, if we specify them in the right way, to define architectures that are as powerful as our previous examples. For example, if you want to simulate an MPNN with this generalized homomorphism counting architecture, you can define a multi-layer DHN where the pattern set is exactly the singleton and the edge. So you're counting rooted homomorphisms in local neighborhoods around nodes exactly for the singleton anti-edge. GHC would be you do one layer in the beginning of this kind of thing, and then normal MPNN message passing. And FMPNNs would be a single layer of this DHN on your pattern set, and then a multi-layer DHN on singleton anti-edge, while our loopy MPNNs would be multi-layer DHNs where we extend this pattern set on each layer, not only singleton and edge, but also with cycles up to length R. And then we are basically in one architecture that can represent all of this. The only problem is it's somehow difficult to train, and we're not really, so the empirical results are not yet up to the expectation that would say, okay, we can omit all that we have done previously and just use this one. Let me conclude with few general insights. I hope I could convince you that homomorphism-based methods work well in theory and practice. In theory, we are able to increase the expressivity of architectures by adding homomorphism counts in reasonable positions, right? And in practice, we have seen that this typically improves the performance over baseline methods where we don't do that. But of course, there's much more that I didn't talk about, right? There's a rich theory linking homomorphism counting and KWL, which is typically used to measure the expressivity of graph neural networks. There's also a very nice way of characterizing expressivity of higher order graph neural networks via homomorphism counts that does not necessarily have to do anything with KWL. So you can basically have a more fine-grained view on expressivity using homomorphism counts. You can obtain actually generalization bounds of GNNs using homomorphism counts, and you can use spasms or homomorphism bases as different patterns to learn powerful graph invariants without explicit message passing. And with this, I have lots of references, of course. But with this, I want to conclude my talk, and I'm happy if you have any questions.
Thank you, Dr. Welke, for the talk. It was very interesting and wonderful talk. We can take the questions, but maybe we can